Welcome back. So today I'm going to be talking about or reviewing what we did last class, okay, which is how GMMs and HMMs are applied to speech signal processing, right? Especially the concept of speech recognition, okay. So if you recall, what we said is that I took the simple problem, I think, of yes and no, right? So if I have only two word vocabulary, right? It's either yes or no, and I will collect a lot of data with people saying the word yes, right? Uh, and similarly, a lot of data with people saying no or something, correct? And this basically is what we call as supervised learning. Okay, so here not only do I know the waveform, I know what was the actual word that was set in the waveform. The reason why this problem is slightly more complicated than the R and the E problem is that now yes has three sounds, right? So there is the ear part, and then the air part, and then the sir part. Similarly, no has two sounds, no and OW, right? So we have to now, how do we partition this signal? Because if you recall, we are going to get some kind of a waveform, right, which has all these three. If I'm talking about yes, all these three sounds, and what I'm going to do is do some kind of a processing which is short time, right? So I'm going to take short intervals of time, the signal, which is 25 milliseconds, for example, and the spacing between them is around 10 milliseconds. These are empirically determined. This has been done through experiments and found to be the best, and each one of them is going to now give me a MEL filter bank feature vector, right? So this is an 80 dimensional log MEL filter bank features, okay. So and therefore for every 10 milliseconds I am going to get this information, but the problem for me is I don't know which of these belong to R, which which of these belong to, when I'm saying the sound yes, which of these belong to the sound ear, which of this belong to the sound eh, and which of this belong to the sound s. Yes, no, yes, right? Yes or no, right? No, right? Two sounds come, right? So therefore we have this information that is missing, okay, and this is somewhat analogous to whatever the missing information about the component in the Gaussian mixture was, okay. So now we have these two levels of uncertainty or missing information, and I will talk about how this relates to the hidden Markov model that we use for weather prediction, where we had the weather conditions, sunny, cloudy and rainy, as being states, and actually observing the grass, which gave some information about the outside weather, even though I could not observe the outside weather, right? So if you recall, there we had the HMM problem in weather, right? In weather, and the basic idea there was very simple. I have my these are my hidden states, right? So these are my hidden states: sunny, cloudy and rainy. These are my hidden states, and what I observe, hidden state, and what are observable are the grass condition, which is either dry or dryish, damp or soggy, right? And there is a certain probability with which, depending on the underlying weather condition, these will be observed, right? So this might be 0.6 here, but the same thing when I do for this guy, right? So this might be like dry, dryish, damp, soggy, right? So this might be only 0.3, and here it might be only the same kind of thing is going to happen, right? So dry might be only 0.05 or something, right? 0.05. So we have this probabilities. These are called the observation probabilities, right? So these are called the observation probabilities. and I also have the transition that can happen between them. So this can go with itself, or with itself, or it can go to cloudy on. So there are this transition probabilities and so on, right? So these are the transition probabilities. Okay. Now we have similar kind of scenario for speech, where the hidden states are nothing but your yeah, s, n, ow, a, e, all these. So these are the phonemes. So the phonemes turn out to be the hidden states, and what you observe, the observable states happen to be what? The MFCC vectors, right? So these are your MFCC vectors, or Mel filter bank vectors. Okay. AT-dimensional log Mel filter bank features, right? So these are your features. So the O1, the O2, the O3, and so on. Okay. So again we can talk about going from here to here, or looping and so on. Okay. So these are going to be your transition probabilities, and again this we learn, and different languages will have different probabilities. Why? Because the probability of following yes is depends on the number of times occurred in a language, and the number of times occurred after and that might be different for different languages. That's called the phonotactics, the order, the sequence in which phonemes occur, how often, or what is the probability given a certain set of phonemes, the next phoneme being something. Okay, so this is like we'll see later, something like a language model of the phonemes. Okay, so this is one part that is learned from the language. So I need a lot of data from the language to capture this. And the other part is the observation probability, right? So in the previous case, I had this being like a discrete process. So I observed each one of the state generated one of those four conditions only. So it was dry, dryish, damp, or soggy, right? With certain probability, the total probability added to 1. It is like a discrete process, right? So if I'm talking about coin tossing, there are only two possible things, right? So it can be any one of those, you know, head or tails, or 0 or 1 if you're talking about random variables or something. Or you can talk about throwing a die and then it's 1 out of the 6, 1 2 3 4 5 6, right? On the other hand, if I'm spinning the wheel or something, right, and I put a chalk mark and I'm asking what angle, so it's continuum, right? So it can be any of those angles in the 360 degrees, or when you talk about in terms of radians, we talk about 2 pi radians and so on, right? So there it's uniform, so it is a continuum, right? So it's a continuous side of a modeling, right? So it will be anywhere from 0 to 360 degrees with a probability of 1 by 360, right? So the total area always has to be 1, correct? So there we talk about delta, the neighborhood of something, to find out the probabilities, correct? So here it was discrete, and I had some values that I could assign 0 0.6, 0 0.3 or something, right? But here, what is the probability of the state or the phoneme generating this particular generating this observation of feature vector? This is somewhat analogous to, this is a 80-dimensional vector. Remember we talked about height and weight, or height and weight and chest size or something, and then we said Norwegian versus Indian versus pygmy, and so then we can have a mixture in that population, because there could be some children, some men, some women, so you need some 3 or 4 Gaussians to model it, and then we could find out what is the likelihood of a particular observation, right? Which is basically one particular measurement of height, weight, and chest size, right? So instead of that, here we are going to take this and we are going to model each of the states with a mixture of Gaussians. Okay. Gaussians. So, and then we can, just like how a particular height and weight measurement I was talking about, evaluating. So here if I took a particular vector O1 and I'm looking at the GMM for IY, so I will be looking at the GMM for I or Y, right? If I'm looking at the GMM for Y, right? Then maybe I will look at what is the probability given this sigma y. These are the parameters of the GMM, right? Parameters of the GMM for IY, for Y, right? The sound Y, and this will basically be the summation I, if I'm talking about 16 Gaussians, some WI, some associated, uh, mu I, right? And then sigma I for the value of for the GMM for IY, or if I'm talking about GMM for the sound n or something, then it will be I equals 1 to 16. If I'm taking a mixture of 16 Gaussians, right? Mu I, for the sound n, right? And sigma I for the sound n, right? The covariance matrix, right? So I basically am going to evaluate this. So that's the way we are. So there are 3 ideas that I've talked about. One is the hidden states in speech. Those are going to be the phonemes. We'll come to a little more fancier version of these states. And given the observation vectors, the observations like the grass are nothing but the Mel-Filter-Bank coefficients or the log Mel-Filter-Bank coefficients, and we are going to model each of these states in terms of a mixture of Gaussians. So these are the 3 things that you have to remember, right? And then similar to the problem that we have dealt with before, that is given that I observe dry, then again dry, then damp, soggy, dryish. Let's say 5 weather day, 5 conditions of the grass on 5 consecutive days. So these are the so then we can look at the D1 first day, D2 second day, D3 third day, D4 fourth day, D5 fifth day, and then I can ask which state sequence best explains, given that previous day was cloudy, right? So previous day was cloudy, right? And then what do I observe here? So on that day I am observing here whatever it is, dry, damp, soggy, right? So dry, damp, soggy, dryish. So these are the days, these are the states. So this is the states. So we are progressing in time, right? Sorry, it should be these are days. So on the right hand side, as you go along the x-axis, it's days. When you go down, these are the states. These are the observations, right? And I can ask, so how many different paths are there? So there are 3 different states, right? And given the 3 different states, how many paths are there? There are 5 different days. So 3 into 3, so 3 to the power of 5 paths, which have these coming from the transition probabilities, and each state probability of each state generating this observation, right? So which is the dry or dryish or something, right? So these are the kinds of things we need. So remember, we always talk about these 2, the observation probability and the transition probability, and together I can find the best path, right? Using what? Using the Viterbi algorithm. And that is basically can be like, first day can be, sunny, right? So So it can be in sunny state. I mean, so I can sort of directly remove this. So this can be going from here, right? So this is sunny or cloudy or rainy, right? So, and then the next day maybe the best path is cloudy, and the third day is sunny, the fourth day is rainy, the fifth day is sunny. So this might be the best path. And therefore I will say that that this sequence of sunny, cloudy, sunny, cloudy, sunny, rainy, sunny is best explaining the data. I hope I chose some, I did randomly. So yeah, it seems like, right. So something sunny is come dampy, but at least I got rainy compared to soggy, right. So these are very high chances. So this is the actual weather pattern. So now I'm predicting that, having observed this, what happened on those 5 days in the weather, right. And the same thing now we are going to look at in terms of the time instance now, T1, right. So time T1, T2, T3, T4, T5, T6, T7, some time instants are there. So this is the way time is progressing, right. And what I'm looking for are the states which are nothing but, sorry, AH could be something IY. In a systematic manner, I will have all these 46 phonemes or whatever it is. And let's say I always start with the silence. Silence is a phoneme. That's also an important sound, right? I don't say anything, so that's an important sound, right? The power of silence, right? So silence, and then all these vowels, and then ka, ka, ga, ga, and all these things, right? So let's say I start with silence. And what I observe are all these guys. So this is the states which are basically modeling the phonemes, right. And what do I observe here are these MFCC or Mel filter bank features, right. So they are the Mel filter bank features, right. So this is O1, O2, O3. How many time frames do we take? 8 of them. O4, O5, O6, O7, O8. Okay, so O8, there are 8 such vectors. Okay, and what we have to do is that we have to, and so again I can start from here. I will erase this part. So for each of them, it should properly explain. So I don't know which one of these guys are there. So AH, IY, EH, K, G, Y, N, something. Okay, all these guys are there. So I might go and say silence to E is correct. Then the next one is E itself remains. Then I get G somewhere. Then I get E somewhere. Then I get somewhere, I don't know. So you can keep on doing something like, so that could be looking for the best path. So given that I have observed, having observed O1, O2, O8, what sequence of phonemes best explain this? Okay, that is the only best explain it. And so I might find out that the best explanation is here, here, a, 1, 2, 4, so 2 plus 3, 5. So this could be my best explanation. And so then we say that this is basically nothing but yes. Okay, so the sound yes is what best explains this particular. So this is how we are going to find out. So what we are going to do is, having observed this and having already calculated all this transition probabilities and the observation probabilities, all that is training part. Okay, once I have this, I find out the best sequence. This is the best acoustic sequence that I mean, this is the best sequence of sounds that explains this data. This is all speech recognition is about, okay. And then given the sound, given the phoneme sequence, right, then I have the lexicon to find out the corresponding words, okay. So, lexicon or the dictionary to tell me what the corresponding words are, okay. So, this is nothing but a kind of a mapping, okay, which tells me for every word in that language, let us say if I have and, so there are three sounds, the, right. When I say good or something, then g, u, the, right, something like good, right. So, so all these are done once by expert phoneticians and so on, and in English it's a little more complicated. Like you can see that you know, as I said before, if I write put, right, so this is the word put, so p, u, t, but if I write but, then it's b, bha, b, bhat, okay. Okay, so this is u, that's okay. So the changes are there, right? But if you look at many of the Indian languages, we are highly phonemic. Pretty much the written part and the expansion in terms of, in fact, each one of the characters in our in the alphabets that we use, they have particular sound, right? A, e, u, right. So, you do have specific ways of saying something. So, there is a relationship between the sound and actual written you know, alphabets or characters of a language, okay. So, Tamil is a slightly different language, right. It has lesser things, so we don't have this aspirations and so on. So, so this is the basic idea, okay. And you know, once you get a fair idea of it, when if you go through the previous lectures, I have dealt quite a bit, you know, put in a lot of material in it. So, please spend some time, you know, review it, and you know, you will, you know, once you read it 2 or 3 times or go listen to what I have said, things will become a little more clearer, okay.